All right, let's find any equivalent fraction to 8/9. Just a quick starter for us. And like I've said before, what I like to do is just pretty much just rewrite the entire fraction as is. But then if I tack zeros onto them, then it works, which means that it doesn't matter how many zeros you tack on, just as long as it's the same amount. So where we start with 80/90ths, now it's 80,000 90,000ths. There we go. And yeah, maybe it'd look better if I made that line longer. So 2.6 multiplying fractions. Now we are actually operating with the fractions. So we need to be able to write or actually do the multiplication, but what we also need to do is be able to simplify them and rewrite fractions as the product of a whole number and a unit fraction. That's just one of the problems that they put in the assignment. I don't think you do this very often in real life, but it's going to be on the assignment, so we have to make it an objective. So remember that multiplication can be shown as repeated addition, right? So like we have up here, yeah, 2 plus 2 plus 2 plus 2 plus 2 is 10. That's true. But also 5 times 2 is 10, and that's what multiplication is. Multiplication is taking this, I'm going to call this a long addition problem, and just making it something a little bit smaller with a new symbol. Because what we're seeing right there, it's really 5 groups of 2, which also means add 2 to itself 5 times. And if you were to do that, then you'd end up with something back at what we started. Now, this is 10, this is 10, and this is 10. So again, it's a matter of what you want. What we're looking for here is just to be able to understand the multiplication of fractions. And that's what's showing down here. 3 times 2/3 is 3 groups of 2/3, which means you're adding 2/3 to itself 3 times. Now, while we haven't gone over addition of fractions in great detail yet, we've seen just a tiny bit of it, and really just the surface of it. We're going to go over what this really means, or even how to do it in a later lesson. But just to understand, this is what multiplication is. We're gonna have some rules to apply to this, even before we get to the addition, because if we start with the addition, it does tend to cause some confusion. So 3 groups of 2/3. So this one, we're going to rewrite this as repeated addition. This is 4 times 9/10. That is really the same as taking 9/10 and adding it to itself 4 times. Again, it'd be like 4 groups of 9/10. So the repeated addition would have the 9/10, but you would have to add it to itself 4 times. So there's 2, 3, 4, boom. So that's 9/10 added to itself 4 times. Okay, so what does this look like as an improper fraction? So I'm going to do a little work here, which is, again, it's kind of front-loading with the addition stuff. So what happens here is, remember the denominators in the fractions tell us the sizes of the pieces, right? So these are tenths, these are tenths, tenths and tenths. These are all tenths. There's 9 of them in each set. So what we do is we say, look, you got tenths, and you're going to take 9 of them and add it to itself 4 times, right? So what this does, and this is getting into the multiplication part of it, the numerator is all we're worried about. It's really 4 groups of 9, 4 times 9, which is 36. So we end up with 36 tenths. I'm not going to simplify that yet, but then as a mixed number, then we could use the division. So, well, I guess I'll show them the simplified form of that. Should be 18/5. There we go. How did I get that? 36 and 10 are both divisible by 2. So we can divide them by 2 and then get 18/5. I'm skipping that math right there, really just for the sake of time. We should have that stuff down. So as a mixed number, you could do the 36 divided by 10. I'm going to go with the 18 divided by 5. And let's see what we get here. So 5 does not go into 1, but it will go into 18 3 times. 3 times 5 is 15, so when we subtract that out, we get a remainder of 3. So my mixed number then, 18/5, I've changed into the whole value in the mixed number is 3. The denominator, we were dividing by 5, so it will remain a 5. And then our remainder 3, that's our numerator. 3 3/5 is what we end up with right here. Now, how do you get 3 3/5? Well, I would start with the improper fraction first. So you keep this in mind. when you're doing your multiplication, if you end with a improper fraction, sometimes it will ask you to change it into a mixed number, but not always, okay? So we have the two answers here. Again, these are all representing the same thing. 9/10 added to itself 4 times, 18/5, and 3 3/5. Three different ways to show the same thing. Actually, we have kind of like 4 and 5 right there, but either way. Now, at the beginning, some students get this a little confused. They say, here's a mixed number. No, mixed numbers do not have parentheses like this. The parentheses indicate that some form of multiplication is in play. So once you see something that looks like a mixed number like this with the parentheses, it's not a mixed number. It is multiplication instead. Okay, multiplying fractions, as long as we have our multiplication down, and I'm not even talking about our multiplication table. It's good to have that down. If you have that memorized, you're in much better shape than those that do not. But to multiply fractions, all we do, you take these two fractions here, and what we end up doing, and I like to show it like this, is I like to make it one big fraction, and we're just multiplying the numerators and denominators. That's it. That's what this is showing. Again, A, B, C, and D. These could be numbers, but then you just multiply the tops together, all the tops, the numerators, and then you multiply all the denominators together. You'll keep this in mind because it's possible that you may be getting this, or you may get this mixed up with stuff you've learned in the past about addition and subtraction. With multiplying fractions, and when we get to division, it'll be the same thing. You do not need common denominators, okay? Because look, these denominators, they're probably different. We're just going to multiply them, that's it. And then if we get to the end and this fraction can be simplified, we will look to simplify it. Whether you use prime factorization or just divisibility rules, doesn't matter. You should be able to simplify the answers at the end. So a problem like this one, let's make it a little bigger. Once again, I'm going to rewrite this problem, even though I'd probably show this a little differently. I'm going to rewrite this problem, and I'm going to take the two numerators, 1 and 1, and I would multiply these to obtain a simplified or multiplied numerator, which is 1. 1 times 1 is 1. If you put 2 there, just be careful. It's not addition, it's multiplication. And then in the denominator, we have 3 and 7. Again, they're separated, so these would be multiplied. 3 times 7 is 21. This fraction cannot be simplified, so I'm not worried about being able to simplify it at this point, but you would always look to see if it could. Now, again, I'm just going to show, this is how I like to do it if I were to do it on my own. Okay, so what I would do is I would take the fraction and then I'd say, look, I'm just going to make this one big fraction, and then I multiply the numerator and denominator, and from here, then I can start solving it, or even simplifying it, or just multiplying numerators and denominators. I still get the same answer, 1 over 21. I'm just showing the work just a little different. Essentially, I'm skipping this step or applying it to the fractions that we had in the beginning. For this lesson, just expect me to do this unless I see that it can be what we call cross-simplified, which we'll get to. All right, so 2/7 times 4/5. Let's multiply these. So once again, I'm going to make this one large fraction where I get to multiply the numerators and denominators. So with this will produce a new fraction in the numerator. I have 2 times 4, which is 8. In the denominator, I have 7 times 5, which is 35. So 8 is divisible by 2, 4 and 8. 35 is only divisible by 7 and 5, which means we have found the simplified form of the multiplied fractions. So here's our cross-simplification stuff. What we can do is simplify the fractions, and I'm talking about fractions here, meaning you can look across different fractions, and you can simplify. This is simplifying at the beginning. Okay, cross-simplification is how you will simplify fractions at the beginning so that hopefully at the end, when you do the multiplication, there is no simplification, which is what's being shown here. So to demonstrate this, let's start here. We got A over B times B over C equals A over C. As it turns out, even though the B's are in different fractions, essentially they're factors of each other if I were to make this a large fraction like this. Now, by crossing these out, these become phantom ones, and so I don't have to show the 1 anymore. So on the top, I'm just left with the A, And in the bottom, I'm just left with the c. That's it. It simplifies what would be the final fraction. Now, even using cross simplification, make sure you always check in the end to see if the final fraction you have can be simplified too. Now, on this next one, a over b times f over a equals f over b. So we can simplify, again, this would be crossways with the a's, right? Because this would be the numerator of the first fraction, and then the denominator of the other fraction, they simplify each other. So again, if we looked at this as one fraction, they're factors of the numerator and denominator, which allow us to do some simplification. It's kind of like what we did with simplification of prime factors, but these don't have to be prime values that can be simplified. So that's another way we can simplify. It's another cross ways to simplify. This last example right here, it's not cross simplification necessarily because they're not cross from each other. But what we notice is that you have an A on the top and then an A on the bottom. But again, they would simplify each other out as a phantom one, just as these A's did and just as these B's did. So again, let's go back to this one. Remember how we simplified the A's out as a phantom one, meaning we don't have to look at it? Well, then what are you left with on the top? The F. What are you left with on the bottom? The B. So it's F over B, and we would call that complete unless it can be further simplified. So it's the same thing over here. Once the A's are a phantom one, so we can't see that anymore. We don't have to look at it anymore. You're left with the C on top and the B on the bottom. It simplifies the fractions either during or at the beginning of the problem rather than waiting at the end of the problem to simplify, which you can do. And you should always check to see if these can, because sometimes we'll miss some cross simplification, and that's okay too, as long as you're checking in the end to make sure it can be simplified at the end. All right, so here's the problem. I'm going to use cross simplification here. And I guess, you know what, I would start with the 20 and the 28 right there, okay? So 20 and 28, I'm going to simplify these because I know they're both divisible by 4. So I'm going to divide them by 4. Some students may say, well, I'm going to divide those by 2, which you could do, okay? But if I divide them by 4, then 20 divided by 4 there would then be 5. So the 5 that I put here in the problem is a replacement of the 20 because I divided it by 4. But if I do it to the top, remember the simplifying of fractions? I got to do it in the bottom. So in the bottom, I've got 28 divided by 4, which would be a 7. So that fully simplifies the 20 and 28. Some of you may have been looking at the 12 and 28 to simplify those, and you could have. I just chose the 20 and 28 to simplify. Now, you could say, well, this is fully simplified. No, it is not. So I'm going to go one step further, even though at this point you could have said, you know what, I'm going to make my final fraction here. I got 5 times 12 in the numerator, which is 60. And in the denominator, I've got 25 times 7. I'm going to skip the math there, but that'd be 175. Now, that is true. That would be 60 175ths, but it is not fully simplified because then you would have to divide those by 5. So, let's make it bigger. So you could, if you wanted to, proceed by saying, you know what, I'm going to take the 60 and divide it by 5, which would be 12. And then I've got the 175 divided by, we'll divide that by 5. So let's do the work over here. 175 divided by 5. 5 doesn't go into 1, but 17 3 times. 3 times 5 is 15. So when I subtract, I get 2 left over. Drop the 5. 5 goes into 25 5 times. So we have nothing remaining here. So the denominator ends up being 35. And this would be considered fully simplified because I can't divide 12 and 35 by the same value. So that's its fully simplified answer. But let's go back. Okay, so let's go back and say, couldn't we have done some cross simplification at this point? Yes, we could have, because I would look at the 5 and the 25 and say, you know what? 5 is divisible by 5. I can divide 5 by 5 to get 1. And 25, I can divide it by 5 as well to get 5. Now, instead of having to simplify in the end, we just have, again, on the top, it'd be 1 times 12 this time, which is 12. And then in the bottom, we got the 5 times 7, which is 35. But that would have been fully simplified. Now, it doesn't matter because, look here, we got 12/35, and here we got 12/35. It does not matter. But I'm showing this one because sometimes what you'll do is you'll simplify, but you won't notice this simplification that we did down here. And so you'd say, well, I got 61/75. You can't leave it like that because it's not fully simplified. You have to fully simplify if you can, which may require some division at the end, or if you notice that there was more division between the factors of the numerators and denominators, you could have done that there as well. Doesn't matter which one you do. It does not. You get to choose. Choose the one that you like the best. Some students don't even like to cross-simplify. They'll do 20 times 12 and 25 times 28. Get those values. I don't know what they are. And then they'll simplify from there by doing repeated division. I don't like that because you're like this one right here. It'd be like doing this over and over and over, like 3-4 times. And I don't want to do that. I want to try to avoid that stuff. All right, so let's cross-simplify this one. Now, again, I'm going to cross-simplify. Maybe I will simplify all the way. Maybe it won't. I don't know. Let's go ahead and find out. So I'm going to start. I notice, and again, this takes some thought. I notice I got a 3 in the numerator and a 24 in the denominator. If you wanted to, just like I've done in the past, you could have, or you don't have to, you can make this one fraction with multiplication on top and bottom, like I'm doing. And that way I know I'm simplifying just the 3 and 24, right? So 3 and 24, they are both divisible by 3. And 3 divided by 3, that becomes 1. 24 divided by 3 becomes an 8. Now, I look at these. Some of you would say the 30 and the 8 can be simplified, which is true. I want to simplify with the 35, though, because here I have a 0 and a 5, and 5 is a pretty easy number to divide with. So I'm going to take the 30 divided by 5 and the 35 also, 2 divided by 5. And let's see what we get. 30 divided by 5 is 6. 35 divided by 5 is 7. All right. Now, you could proceed from this point, but I notice that 6 is divisible by 2, and 8 also is divisible by 2. So 6 divided by 2 would be 3. 8 divided by 2 would be 4. Okay, because you can simplify straight up and down. You can simplify crossways or crossways. It doesn't matter. But now I should get a final fraction that cannot be simplified any further. In the top, I've got 1 times 3, so that's my new top or numerator. In the denominator, I've got 7 times 4, which is 28. And again, that's good enough to call this good because 3 is only divisible by 1 and itself. 28 is not divisible by 3, but 1's okay, but we're not concerned about 1. So that cross-simplifies right there, all right? Now to go back, and I'm going to skip some steps here. Let's say that you were like, you know what, I just want to multiply these out and then see what I get. Okay, so again, I'm going to skip some of the multiplication here. But in the top, you'd have 90, and then 35 times 24, 840. And yes, I use a calculator to do that. But what's required here is some simplification. Now, you could say, well, these ones ends in 0, which just happens to be that way, so you can actually make those zeros a phantom 1 and just make it 9 over 84 and then simplify from there. But again, it's like, well, what do you simplify this by? You can't divide by 9. You could divide by 3, but again, you take a little bit of experience there to say, well, 8 plus 4 is 12, so 84 is divisible by 3. 9 is already divisible by 3, and then divide by 3. But even then, you're using long division to figure out what 84 divided by 3 is in order to get your 28. Okay, so keep that in mind. This one only worked out. Sometimes they're just really nasty numbers. So you won't be able to cross out those zeros, and then you got even more work on your hand, more division involved. I highly recommend that you can use this cross simplification in the beginning because if you can, it'll save you a lot of long division, which I would try to avoid. If we see a fraction over 1, we know that it's just all a number, whatever the numerator is. But if we see a number all by itself, we can make it a fraction, which will allow us then to use the multiplication of fractions. Because if we see something like this, which I think we saw already, 4 times 9/10. not only is it possible we mix this up as a mixed number, which we don't want you to do, but some students won't know that it's really 4 over 1 times 9 over 10, and then you make it one big fraction multiplying the numerators and denominators. Here, of course, the 4 and 10 would simplify. I'm not going to do the simplification. I guess I will show the answer. It'd be 18/5, which we've seen already, but again, if you see a number like we had here before, just a regular number, a whole number multiplied by a fraction, I would make it a fraction over 1, which allows us, which is what this is. It's like the identity property of division. If you see a number, you can always make it over 1. So, a problem like this one, yeah, that 9, I'm going to make it 9 over 1. In fact, some students would even like to rewrite this as one big fraction, 9 times 1 over 1 times 9. And that'd be fine too. I'm going to work with the original though. So in the tops, I've got 9s, right? So the 9, you know what? I can divide that by 9. Same with this 9. So 9 divided by 9 is 1, and 9 divided by 9 is 1. You could simplify the 1s, but it's really not going to make a difference. As it turns out, in the numerator, 1 times 1 is 1. In the denominator, 1 times 1 is 1. And anything divided by 1 is itself. So really, I'm just going to say this ends up being a 1. Now, you could have done the same thing there below. You could have just said, well, this 9 and 9 are both divisible by 9, which are 1s. And then you could have gotten the final answer 1 as well. I skipped a couple steps there too, but I just need you to get the point on this, okay? Because if you see a number being multiplied by a fraction, just make it a fraction over 1, and then do your math. It won't always be this clear, or I'm going to call this easy, but the process will pretty much remain the same. Yeah, so this, right? You can think about adding 37/45 30 times. I don't want to write that out. That's garbage. It's too much writing. So if you do, that's fine. I'm just not going to do it. So I'm going to use multiplication here, and I'm going to say, you know what? 30 over 1 times 37/45. All right, I got my two fractions separated, but let's see if we can start doing some simplification here, okay? So I would look at the 30 and 45. 37 is kind of a weird number. It's not a multiple of anything specific, which is why it's prime. But 30 and 45 are both divisible by 5, at least. Perhaps more, let's find out. But 30 divided by 5 would be 6. 45 divided by 5 would be 9. So yeah, we could have divided by more, because now the 6 and 9 are both divisible by 3. So we'll cross simplify these as well. 6 divided by 3, there is 2. 9 divided by 3 is 3. And now I'm ready to do my multiplication for my final fraction. So in the top, we've got 2 times 37, which I'm going to have to do the work down here. 37 times 2. 2 times 7 is 14. Carry the 1. 2 times 3 is 6, but add the 1 makes 7. 74. That's my new numerator. In the denominator, 1 times 3, hey, that's easy enough. 3. Okay, and that's how I'm going to leave this. I know we looked at a problem that had this changed to a mixed number, which you could do with long division, but I'm just going to keep it as is. So here's a diagram. You may see diagrams like this on the assignment, and we just got to go through the question. Let's see if we can answer them. How many total small rectangles are in the full unit square? So, you know, we just go in here and just count them. So I see 1, 2, 3, 4, 5, 6, 7. 7 in each row, and then there's 3 rows. So really, I would show this as 3 rows of 7, which would be 21 of those small rectangles. So what is the area of the shaded region? Okay, well, it's asking really how many triangles are shaded. So again, we can count those. Not too bad. Let's see how many we got. 1, 2, 3, 4, 5, and then there's 2 rows. So again, I would show this as 2 rows of 5, which would be 10. You could count all 10 if you'd like, but 10. 10 of those triangles are shaded. In this case, red. So what is the width of the shaded region? Okay, the shaded region, I guess we already counted it. That was 5. It's 5 units here. So that is my width what is the height of the shaded region? Again, we already counted that as well, but that would be 2. So write an equation expressing the product of 5/7 and 2/3. Why is it 5/7 and 2/3? Well, it's because up here at the top, let's give ourselves a little space there. Up here at the top, we counted that it was 7 rectangles wide. And then here on the, well, I'll do it on the right, it was 3 rectangles tall. So how is it 5/7 then? Well, of the 7, we got 5 shaded widthwise right here. So 5 are shaded out of 7 wide. So that's where the 5/7 comes in. And then for the, I'm going to call this the height. It's 3 tall, so we're going to make it a fraction out of 3. And only 2 of those are shaded, right? Because we can see 2 out of the 3 total. So that's why they're saying it's the product. It's 5/7 times 2/3. Now the reason I'm showing that is just because that's how we get these values. Okay, you got 5 out of 7 and 2 out of the 3. 5 out of the 7. There we go. But it's saying write an equation expressing the product of 5/7 and 2/3. Well, that's what this is showing you. Why is it multiplication though? It's because it's multiplication. It's because it's the area. The area of that shape. So what we did is we took the 5/7 up there, and we took the 2/3 as well. And what we found was the area between these two. And you find area by taking length and then multiplying it by width. So what would the actual product be? Well, you could just do straight multiplication on this, or you can kind of see what we have on the inside here. Excuse me. And that is that in there we have 10 shaded boxes. So it's 10 shaded boxes out of however many boxes there were in the beginning, which it says up here was 21. So you see, really all we did is we took the numerators and multiplied them. 5 times 2 is 10, and 7 times 3 is 21. All right, for problems like this one, which again you're going to expect to see, we have 2 different shapes here. Well, 2 different parts that when we combine, we get this area right here. And so you got pink, you got blue, and then you got, once they mix, you get purple. Excuse me. So what fraction of the entire grid is shaded pink? So up here we see, in terms of the pink boxes, you could just count them, but really we're just looking at the bars. So for pink bars, which I'm looking at more in a kind of a vertical fashion there, we get this one. Sorry, this one. There we go. And this one. That's 2. 2 bars, like we said. There's 2 parts, but it's a fraction, of course, out of what would have been 3, 4, 5, 6, 7 bars. So 2/7 is shaded pink, and that's where this 2/7 comes from. What fraction of the entire grid is shaded blue? Well, here's our blue shape right there. This one is going to be in rows, so the pink bars, again, we said those were bars. Really, you're welcome to call those probably columns, maybe a little bit more technical. But then we have the rows of blue bars. So how many are there? Well, 1, 2 rows are shaded. Again, this goes back to our shading here, which would say there's 1, and there's 2. Well, that's 2 shaded, so we'd say how many shaded blue? 2 out of, well, there were 3 rows. Okay, so it's 2 out of 3. So that's the fraction of the entire grid that's shaded blue and then pink. Then it says, well, how many bars are shaded purple? And it's important for us not to get purple and pink mixed up, but this would be 1, 2, 3, 4. 4 of the rectangles are shaded purple. How many small rectangles total are there in the large grid? Well, it is a 3 by 7 grid. So you're welcome to count these, but that means that there should be 3 times 7, 21 total small rectangles in the grid. Now, what this is going to do is it will provide us with our final fraction, because up here we had 2 times 2, which is 4, and that's the 4 that we got here. And then we just did the 7 times 3 to get the 21. That's when it's asking how many bars are actually in the grid. So you see, if we took away some of the lines here in this one, and then these vertical lines on this one, then you see you combine them, and that tells you how small the pieces are in the end with the multiplication. So these are sevenths, these are thirds. When you combine them with multiplication, you've made the pieces much, much smaller. Notice, though, that the whole thing, though, has not been made smaller. All that we do is we add more lines in here to make the individual pieces still the same size, but smaller. In this case, size 21ths, and only 4 of them are shaded both colors. Now, along these lines, I would never do this on my own if I was looking at fractions. I just wouldn't do it. What I would do is just stick to our rules where we say multiply the numerators and denominators. Maybe use some cross simplification if you can find it, but there wasn't any in here, and then we would have had that fraction anyways. This is just hopefully helping you to understand what is happening in the multiplication. So right here, the D stands for denominator. You can click the up and down arrows to change the denominator for each fraction. You can drag the circle left and right or up and down to change the number you are representing. So you got to be careful here. Here are 2 factors. This is my first factor, 3/5. 4/7 is my second factor. Now the reason why we need both of these is because when you start messing with this D over here for this line, that has to be the first factor. If you make the second factor this, when I tried in the assignment, it marked me wrong. And then your denominator for this side right here is your second factor, okay? So my first factor, which has a denominator of 5, means that I need the D here, the denominator, to equal 5. So you'd have to click up until it shows 5, and that's going to change it to look something that kind of looks like this. Okay, that's what I'm going to stick with. And, well, is that perfect? It's not, and I don't care, all right? So I'm just going to leave it like that. And, yeah, once you do that, it's going to split this up, but we're not going to need that. So I'm not, and you'd have some lines here, but I'm not worried about that. Okay, now again, this 5 was from the first factor denominator, but the second factor's denominator, the fraction, has a denominator of 7. So this denominator over here, you got to click the up button until you get to 7. So then you get something that looks like this. Okay, so we're going to see something like this here. But then, you see they've given you some area to put in here. So for my 5, I've got to get to 3 parts down, okay? So that's going to be 1, 2, 3. You could just count lines, 1, 2, 3. So I've got to go 3 parts to the right over there, which means I take this dot here and drag it over to this line, whichever the third one is. And then this one, this dot right here, we've got to have 4 of those parts. So I've got to count up. That'd be 1, 2, 3, 4, which means I need that dot to be right here. Now what's going to happen is as you move those, you're now going to have this shaded area, and it should be green in there, something like this. And that's what you have to have, because remember this was let's go back here, 1, 2, 3, 4. Yeah, 4 parts. 3 parts on the first factor because of the numerator, 4 parts on the second factor because of the numerator. The denominator tells you how many parts to split it up into. Now, that's a 4 by 3. That would represent 12 parts, and I know it's not really asking for this. But if you were to work with this fraction, again, you see 12 shaded green parts out of, see this one right here? You'd have to do, well, we made it 5 by 7. And 5 times 7 would be 35. If I'd drawn these better, they'd look like squares. But I did the best I could. You could count these. There'd be 35 of them, 12 of them shaded, 12 shaded out of 35. But again, this comes from the 3 times 4 to get 12, and then 5 times 7 to get 35. Again, none of these simplify, which is good for us right now just to see why this is happening and also to see how to do these problems in the assignment. But really, you should look for some simplification in the future. All right, on this one, the green rod is times as long as the red rod. The red rod is times as long as the green rod. Oh, so we don't know how many times they are of each other. So let's look, we got the red and green. So I made these a little bit bigger, but let's even specify what this is asking for. So it's asking, the first one, the green rod is blank times as long as the red rod. It's really asking how many red rods to make a green, there we go, rod, question. And then same with the next question, the red rod is blank times as long as the green rod. It just switches those, so that one's asking how many green rods to make a red rod. There we go, question mark. Okay, so yeah, there should have been some blanks there. Is blank times as long, is blank times long. There we go. So sorry, where those are, there should have been blanks there. So we look at this and we need to acknowledge that they've given us some lines to work with here, okay? So if we look at this as parts, we could actually break up the red and green this way, and then this way, like this. And yes, I apologize, my lines are not perfect. But the first question, how many red rods to make a green rod? Well, we know that it will take the full red rod here to make up this part of the green rod. But then we have this one extra square, which is, well, I'll say it's this square right here, okay? So if I were to take this square and then put it here on the green rod, then it would be a complete green rod. So how much of the red rod is that? Well, this was half of it because it's made up of two parts. We just had one of them. But meanwhile, we have the full red rod right there. So as a mixed number, you could say it's 1.5. Or in terms of halves, you could just count. You'd have 1, 2, 3, 3 of the halves. And that would make up one full green rod. Now, I don't know which one it's going to ask for on the assignment, so I'm giving you both the mixed number and the improper fraction. Okay, now the next question, it's saying how many green rods to make a red rod. Well, it's not even a full green rod, right? So again, we have to look at how this is broken up. So I'd look at this line and this line. So the green bar or rod is 1, 2, 3 rods, right? But the red one is only taking up 1, 2 of those parts. So the green is split up into thirds. And the red is showing 2 of the thirds. So that would be 2/3. So how many green rods to make a red rod? Again, it's not even a full green rod, it's 2/3 of that green rod. So since it's a proper fraction, there's no need to show it in two different forms. Improper fractions can be shown as mixed numbers, but proper fractions just stay as they are. So unit fraction is a fraction where the numerator is a 1. The numerator is 1. Okay, so we're going to have to keep that in mind. If we see a fraction, we don't really care what's on the bottom, but what we should see on the top is a 1. Now, sometimes this is, I mean, it can be very useful, but what happens is you can take a fraction, any fraction, you know, I'll use some abstractness here. So let's say that you had something like A over B. Okay, and again, this would represent numbers. What it's going to say is it wants a whole number times a unit fraction. Okay, so what we're going to do is what we would do is the top tells you how many of the pieces there are, and then the denominator tells you what the sizes of the pieces are. So what you can do is you can say, you know what, you're going to keep the same size pieces, and what you can do is make it one of them, but the numerator there would have been how many of that amount of fraction you have. So you just multiply those two together and then you have your answer. So that brings us to this example. Write the following fraction as the product of a whole number and a unit fraction. So I look at my 11/13ths, so I know the sizes of the pieces can't change. I need to keep this as 13ths, but I want to look at this as a unit fraction, which would be the 1/13th. And what makes this unit fraction? It's the numerator, it's a 1. All right, but what happens to that 11? Well, we just take it out front and then we simply multiply it by it. So this is like having 11 groups of 1/13ths, which is what this is saying too, right? You have 11 pieces that are size 13ths. Same exact thing, just shown in two different ways. This is what they're looking for on these types of problems. So what do you think about this one? It's going to work pretty much the same. We want to write the fraction as the product of a whole number and a unit fraction. Okay. Well, let's give ourselves a little bit more space, but once again, I have 21th size pieces, so I'm going to keep 21th size pieces, but I'm going to change this into a unit fraction as 1/21. Because my unit fraction has to keep a 1 as its numerator. But again, how many of those 1/21ths would we have? Well, back here it was saying it was 17 of those 21th size pieces. So I simply take that 17, move it out front, and then I can multiply these two together. Now this may be useful. I don't use this strategy very often when I work with my fractions, but it's possible that you can if you wanted to. Okay. Again, usually when I'm looking at fractions, this looks to me like it'd be more of a cross simplification type thing. And I would rather use cross simplification than to take a fraction and change it into its unit fraction and whole number equivalent. Okay, more or less or equal, fraction multiplication factors. When a factor is more than 1, the product is automatically more than the other factor. When a factor is less than 1, the product is automatically less than the other factor. So just in case we've forgotten, if you look at a multiplication problem, let's go back to 5 times 2 because it's a fairly common multiplication that we see. 5 and 2 are what we call factors. And then whatever it equals is what we would call the product. And in this case, that product would be 10. So what it's saying is that you got 2 factors, okay? Now, fractionally, if we look at one of the factors, and of course it's not this particular problem, the example at the bottom, but if one of the factors is more than 1, then the product will be more than the other factor. So, for example, this one, 5, if I relate 2 to 5, 5 is more than 1, so our product will be more than 2. Or also 2 is more than 1, so the product between 2 and 5 will be more than 5 as well. It goes both ways. Now, on the other hand, if one of the factors was less than 1, which can happen from time to time, then the product is automatically going to be less than the other factor. So if you took 2 factors, so let's take a couple factors here. I'll take something easy like 100, okay? And let's say multiply it by something less than 1, like a common value that's less than 1 is 1/2. Well, if I multiply this by 1/2, okay, so 1/2 is less than 1, so the product has to be less than 100. So right here, just so we know what that product is, it would be 50. I'm skipping some work there, of course. Now you could look at it the other way too. You could say, well, 100 is greater than 1, so if I multiply it by 1/2, the product would be greater than 1/2. Both of those are true. Both those statements are true, okay? So depending on how it's worded on the assignment, you're looking for a factor. If one of the factors is more than 1, usually they're going to be shown as fractions. Like the 2 there, it could have been shown as like 2/1, okay? So that would be considered a fraction that is bigger than 1, which really means that you're looking for a improper fraction, but a mixed number will do, all right? And then down here where we see if one of the factors is less than 1, then you would just have a proper fraction. And that's what we can expect to see on this assignment. So that's all it's saying. And if I guess this is the other one. Maybe one of the factors is actually a 1. Well, that's the multiplicative identity. So if you multiply anything by 1, you just get itself back. All right, so this one, we're not going to do the calculation. We just want to know if the product is going to be more than or less than, maybe possibly, it could be equal to 14. Well, we look at the 14. Okay, there's my 14 right there. and I look at the other factor. Here's my other factor. Well, that factor is less than 1, which also makes it a proper fraction, which also means that my answer will be less than 14. So there I go. And that's all you got to do for these types of problems. You just got to determine if it's less than, equal to, or more than. You're just looking at, they're going to give you one of the factors. They'll say, look at this factor right here, like I did with 14. Now look at the other factor, okay? Is that going to produce a product that is more than, less than, or equal to the factor we were looking at? Well, you just got to see, is it a proper fraction? Is it less than 1? Is it 1, or is it greater than 1, which would make it either a mixed number or an improper fraction. That's it. We'll do the same thing on this one without doing the calculation for 19/17 times 6. Should you get an answer more than, less than, or equal to 6? Well, I look at this fraction right here, or the factor rather. I'm relating it to the 6, so I know I'm relating it to 6. I look at the other factor, 19/17. Well, that one right there is an improper fraction. And since it is an improper fraction, I know that my answer will be more than 6. And again, that's because 19/17 is more than 1. And then I know that the answer is going to be more than the other factor. All right, that's 2.6 for us, multiplying fractions. So our objectives, we should be able to multiply fractions, but also rewrite fractions as the product of a whole number and a unit fraction. In addition to that, we also saw some modeling with like the bars and things like that. So that'll be required on the assignment, but ultimately, if you can just multiply the fractions, you'll be really well off in the future too.